Hello everyone, a very warm welcome to Diksha Karnataka YouTube channel. I'm Aditi, your physics teacher, and I'm back with another solution of model question paper. Paper number 3 today for physics for your PU2 boards. Now we are given 3 of these from Karnataka boards, 2 of whose solutions are already there on our YouTube channel. You can go check them out. Today we'll be solving the third one. Now we know how important these are for your PU2 boards. A lot of questions can directly come into your board, so make sure you watch those 2 videos as well and you watch today's videos. We'll see all 45 questions from MCQs to fill in the blanks to 2, 3, 4, 5 markers with the definition, with the derivations, everything in this one single video. Correct? So let's start with the very first question. Question number 1, which says the electrostatic force between a pair of unlike and like charges respectively are what? So we just very simple question. We know for unlike charges the force is attractive and for like charges the force is repulsive. Very easy question. So the correct option will be option number C. Make sure to tick the right option. It might seem silly to you right now, but if you tick repulsive and attractive because of some silly mistake, that will cost you 1 mark. So be very careful about that. Moving on to the second question, the electric potential at the surface of a conducting charged spherical shell. We have a conducting charged spherical shell whose electric potential at the surface is 20 volt. The electric potential at the center of the shell is what? Again, easy but a tricky question. You need to remember that electric potential for a conducting shell, it remains same inside the shell. So whatever the potential is at the surface, the same will be there at the center. So the correct option will be option number C, that is 20 volt. Correct? Third question says, as the temperature increases, the resistivity of metal increases and semiconductor decreases. Metals decreases and semiconductor increases. Both metals and semiconductor increases. Metal remain constant but semiconductor decreases. So for this we know as the temperature increases, the flow of electron in metals increases, but because of that flow, collision also increases. That in turn increases the resistivity. So for metals, the resistivity increases as temperature increases. But for semiconductors, we know for semiconductors resistivity decreases because as we increase the temperature, the flow of charges increases without the collision. So conductivity increases but resistivity decreases as the temperature increases. So for metals it increases, semiconductor it decreases. So the correct option will be option A. Correct? Moving on to the fourth question. A charged particle moving in a circular path in a uniform magnetic field. Choose the wrong statement among the following. Radius of the circular path varies directly with its velocity. Okay. Radius of the circular path varies inversely with the magnetic field. Frequency of revolution varies directly with the charge, or frequency of revolution varies directly with the kinetic energy of charge. We know the formula of this. F equals to QVB on a charge placed in a magnetic field. So if it is rotating in a circular path, so centripetal force will be equal to QVB, and from here we'll get the formula mv divided by qb. So for radius it says varies directly with its velocity. That is correct. Varies inversely with the magnetic field. So both of these options are correct. So we need to tell the wrong statement. For frequency we know it is qb by 2 pi m, similar to the frequency of cyclotron. So what it says, frequency of revolution varies directly with the charge. It varies directly with the charge, true. It varies directly with kinetic energy of charge. There is no mention of kinetic energy in this formula, right? So the wrong statement is the D statement, and that is our answer. Okay. Fifth question says, a magnetic dipole of magnetic moment is placed in a uniform magnetic field. such that theta is the angle between magnetic field and its magnetic moment if the magnetic dipole is in stable equilibrium position. So for stable equilibrium, we directly know, even without thinking, for stable equilibrium theta will be 0 degrees, correct? So the correct option is 0 degrees for the 5th question. Moving on to the next, that is 6th question. So for 6th questions, the dimensions of inductance is, we are given with 4 options, that is A, B, C, D. You can see the questions. How to solve this now, how to look at these will be, now inductance we know is magnetic flux divided by current, right? So magnetic flux, that is phi, is B dot A, or we can write BA cos theta, correct? On the other hand, B equals to what? Just like we saw in the previous question, F equals to QVB. So B will be F divided by Q into V. Now we can find the dimensions of B from here. This is very easy. Dimensions of force, dimensions of charge, and dimensions of velocity. If you want to do that, this will be M1 L1 T minus 2. For charge, it is current into time, that is ampere into time, and for velocity it is L1 T minus 1. So this cancels, and the dimensions of magnetic field we will get is M1 here M1 L1 also cancels out, and we'll get A1 T minus 2. We'll put this definition, this dimension here, that is B into A. Dimensions of A is area, that is L square, correct? So dimensions of phi will be what? M1 L2 T minus 2 A1, correct? And for inductance, this is magnetic flux divided by current, and for current the dimensions are simply A. So that is inductance will be equal to M1 L2 T minus 2 A1 divided by A1. Is there some mistake? Let me just see. Okay, so here is A1. When it goes up, it becomes minus 1. So here is minus 1, minus 1. So this whole terms becomes what? M1 L2 T minus 2 A minus 2. Correct? So that is the correct option will be M1 L2 T minus 2 A minus 2. I told you I'll do all the solutions. I'll give you all the solutions. Okay? Okay, moving on to the 7th question, that is, different devices connected to an AC source are listed in the first column. We have resistor, inductor, and capacitor. In the second, we have different phases column and different phase relations of electric current with the voltage. So these are relationships of electric current, phase relations of electric current with voltage that are listed in second volume. Choose the correct match. This is very easy. For resistor, we know the voltage and electric current are in phase with each other. So that is, the electric current is in phase with voltage. So first is matching with Q. For inductor, the electric current lags behind the voltage, that is P by phase, pi by 2. So second, that is inductor, it matches with P, and then definitely third will match with R, and that is our option number C. Correct? Okay, moving on to the next question, that is 8th. Expression for displacement current is given by. Now this is the most simple and yet most repeated topic of your of this chapter, the definition or the formula of displacement current. So that is simply epsilon naught d phi by dt. Correct? So that will be our option number A. Very simple but very repeated question. Okay, answer number A. 9th question, the objective lens of a refracting telescope is a dash, and the magnifying power of the telescope for normal adjustment is what? So we definitely know the objective lens is nothing but convex lens. All the options even have convex lens in them. Now magnifying power for normal adjustment we know that is the focal length of objective divided by focal length of eyepiece. So our correct option will be, and the objective for normal adjustment, the telescope has large aperture. correct? The objective lens has larger aperture, so make sure to look at these values as well, because these are same, correct? So it has larger aperture, so the correct option will be option number C, that is convex lens of large aperture having magnifying power FO divided by FE, correct? Moving on to the 10th question, statement question. Among the two given statements, statement 1 says wavefront is the surface of constant phase. Seems correct. Statement 2, when a plane wavefront is passed through a thin prism, it emerges out as a spherical wavefront. Is that correct or not? You can tell me in the comment section, is this correct or not? Okay, have you? Okay, this second statement is actually not true, because we know that spherical wavefront is given by not the prism but the lenses, correct? So whenever a plane wavefront passes through a lens, or it goes through, it refracts, it converts into a spherical wavefront by the lenses, not the prisms. Okay, so statement 1 is definitely correct, but statement 2 is wrong. Okay, moving on to the next, that is 11th question. In photoelectric effect experiment, the graph of a physical quantity y versus a physical quantity x is a straight line passing through a region. I just love this topic. So photoelectric effect, we know that photon hits a surface, a conductor, a metal surface, and ejects electrons. Now we have lots of terms in them: photoelectric current, frequency, intensity. So they are saying the graph between y and x. So the graph between y and x is a straight line. Now photoelectric current, if we have to see, photoelectric current varies linearly with what? Like current varies linearly, not with frequency, not with potential, not with the frequency of incident radiation, but it varies linearly with intensity of incident radiation. So this fourth option is true, that is option number D, correct? Option number D. Moving on to the 12th. An alpha particle, a proton and an electron and a neutron are moving with the same velocity. Then the particle having longest de Broglie wavelength will be. So de Broglie wavelength is simply given by h by mv, correct? Lambda, so lambda is inversely proportional to their mass, and out of these all we know electron is the lightest, so electron is the lightest, so its wavelength will be longest. So we have to tell what is the longest wavelength, and that is of electron, correct? Okay, 13th question, it says Rutherford's nuclear model of atom fails to explain what? Large angle scattering of alpha particles, charge distribution in an atom, energy of electrons revolving around the nucleus, or a region of line spectra of hydrogen atom. Although these two it quite explained, but energy of electrons revolving around the nucleus was also a bit questionable, because it was not as explained why they are quantized or not. But the main point it couldn't explain was the hydrogen spectra, its origin. So the correct option will be origin of line spectra of hydrogen atom. Okay, that is option number D. 14th question, it says nuclear binding energy per nucleon is, where A is the mass number of the nucleus, more for heavy nuclei, more for lighter nuclei, less for both light and heavy nuclei, independent of mass number. So it's definitely not independent of mass number. And we have the graph, it's something like this, so it's definitely less for heavy as well as light nuclei. So the correct option will be option number C. Okay, moving on down the last MCQ, that is, if Ne and Nh are the number of free electrons and holes respectively, then in case of intrinsic semiconductor, very easy, intrinsic semiconductor, we know the definition of intrinsic semiconductor holds that the number of holes and number of electrons are equal, are generated in pairs. So there are equal number of holes and equal number of electrons. That is our option number A. So we are done with our MCQs. Moving towards the fill in the blanks. Fill in the blanks for the first says, okay, an example, you are already given with some of the options, but they are there to confuse you. So try to solve the fill in the blanks by yourself first, okay. An example of of dimensionless quantity is, out of these two, what are these given? What is the dimensionless quantity? It is definitely, ma'am, susceptibility. So that is magnetic susceptibility. Correct? A current carrying coil stores energy in the form of what? We know a current where there is a current is generated. If a current is passed, magnetic field gets generated. We are studying it from 10th class. So that is a current carrying coil stores energy in the form of magnetic field. Correct? Magnetic field. Next, the power factor of a LCR circuit at resonance. So at resonance, power factor is equal to unity, that is 1. Correct? The principle of optical fiber is very easy, ma'am, that is total internal reflection. This is given. Okay, I'll write the numbers. This is 19th, 18th, this is 17th, and this one is 16th. For 20th, the bending of light around the corners and entering into geometrical shadow and region is called. See, what is left? Electric field and diffraction. So obviously electric field is not the answer to this question. So this is definitely diffraction. Sorry for my writing. This is okay. So this is diffraction. Okay, moving on to the next question. We are moving to the 2 marks questions here. 21st question, it says define electric flux through an area element. Mention its SI units. Electric flux in general, we know it's just number of electric field lines passing through that given area, that area element. Correct? So this is just a basic explanation. Number of electric field lines passing through a given area is called electric flux. It is the dot product of electric field vector and the area vector of that area element. Correct? And it's SI, since it's a dot product of electric field and area vector, electric field into area, electric field is nothing but force by charge into area. So this will be Newton per coulomb meter square. Correct? Moving on to the 22nd question. What is meant by equipotential surface? Draw equipotential surfaces of an electric dipole. Now equipotential surface, we all know, is a surface on which at each point potential remains same. That is it. That is it. So what is meant by equipotential surface? A surface on which electric potential is same at all points. Hence no work is done in moving a charge on these surfaces. Correct? This is not the answer to this. Okay, we are asked to draw equipotential of a surface of electric dipole. So this is my dipole. Let's draw the dipole first. This is dipole, and simply this will be the electric field lines around the dipole, right? We know that from plus q charge they'll go outside, for minus q charge they'll be coming inside. So this will be the direction of electric field lines. Correct? But equipotential surfaces, because of these electric field lines, will be the equipotential surfaces of a dipole will be something like this, around plus q charge and around minus q charge as well. So these yellow ones, both of these are equipotential surfaces. Correct? Understood? Okay, moving on to the next question. Write any 2 limitations of Ohm's law. So Ohm's law, we know, very important law in our whole electricity department, but 2 limitations are, it is only applicable for ohmic conductors. What are ohmic conductors? For which the resistance remains same. And the second thing, it says Ohm's law is valid only when physical quantities remain same. What does that mean? That means temperature should not change, pressure should not change of the conductor we are measuring the Ohm's law for. correct? Okay, moving on. So here for ohmic conductors, so they are not valid for semiconductors. Okay, in case of semiconductors, we cannot use Ohm's law, correct? Moving on to the next question. 24th question says, give the vector form of Biot-Savart's law and explain the terms. So Biot-Savart's law basically talks about the magnetic field due to an length element where the current is passing from, correct? So the magnetic field at a point due to a small current element I dl. So dl is that small length we are talking about. From that small length the current is passing. Because of that small length, because of the current in that small length, at some distance, at a point there is a magnetic field getting generated. That magnetic field is given by, let's say this is my element and this is the dl and current is passing. Because of this element a magnetic field is generated at this point P. So that is being given by Biot-Savart's law, which says that dB will be mu naught by 4 pi I in dl cross r. R is the distance of this element from the point, that is unit vector of r, which gives the direction, divided by r square. Very easy. So dB is the magnitude of magnetic field due to this current element. Mu naught is permeability of free space, we know that. Current flowing through the conductor. L is the vector length element of the conductor in the direction of current. Although we are not directly using length here, we are using dl, so it's just a length element of the whole conductor, a small part of that, small length of that whole conductor. And r is the distance between the current element and the point where the field is measured, correct? Okay, moving on to 25th question. What is AC generator? What is its working principle? AC generator, ma'am, it's very easy. What does it do? It converts mechanical energy into electrical energy in the form of AC, in the form of alternating current. So it is a device which converts mechanical energy into electrical energy in the form of alternating current. Now they are asking about its working principle, so we know it definitely works on the principle of electromagnetic induction. Make sure you remember this point. It works on the principle of electromagnetic induction. How? So we have a coil. When this coil is rotated in a uniform magnetic field, what happens? A change in magnetic flux is generated because of that rotation, and so magnetic flux linked to that coil is continuously changing, thereby inducing an EMF, motional EMF we can say, due to that in the coil. Understood? This is, we are doing 2 marker questions. Moving on to 26. List any 2 uses of infrared rays. Infrared rays are basically used in TV or AC remotes. We have or controllers for wireless signal transmission. Very easy. And you must have seen that we use infrared cameras for night vision. You must have heard about that. So that is also is one of the uses of infrared rays. These are used to detect here radiations in night vision cameras and thermal imaging devices. Correct? Okay, moving on to the next, that is 27th. The radius of the innermost electron orbit of a hydrogen atom is 5.3. Now determine the radius of n equals to 2 orbit. So we just know the relationship, that is R1 by R2 equals to N1 by N2 and its whole square. Don't forget this part. R1 is given the radius of innermost electron orbit. So for 1 it is given 5.3 into 10 raised to power minus 11 meters. R2 we need to find, determine the radius, and 2 is also given, 2 square. Correct? This equal to is not needed. So just to find R2, we can directly find out R2 from here. 4 into 5.3 into 10 raised to power minus 11. Now this will be 21.2 into 10 raised to power minus 11 meters. Very easy question for your PU2 boards. Okay. 28th question, mention any two differences between half wave and full wave rectifiers. From the name, it justifies that half wave converts the half cycle of AC into DC, and full wave rectifier converts both half and both the positive and negative cycle into from AC into DC, converts only half cycle of AC into DC, convert both half as well as full cycle of AC into DC. In half cycle, only one diode is connected and a load resistance is connected, but in full wave rectifier, two diodes are connected with the load resistance. Correct? That is it for this question. 29th question. Okay, now we are moving to 3 marker questions, very important questions. These are the questions which can give you a lot of marks, okay, and they don't require much more explanation, but they give you numbers, so they're very great part of this paper. Okay, define linear charge density, mention the expression for electric field at a point due to an infinite line of charge, and explain the terms. So basically, linear charge density, we just know charge per unit length. That is it. That is the only thing. So it is the total charge per unit length given by lambda, that is Q by L. Now electric field, they are just asking to mention this expression. So we are just mentioning the expression, which is electric field due to a point due to infinite line of charge will be lambda by 2 pi epsilon naught r. Correct? That is it. You don't have to solve it because they have just asked to mention. You do have to explain these terms. This is simply electric field. This is our linear charge density. R is the distance of that element from the point where we are measuring the electric field. That is it. That is it for this. And epsilon naught, you can just write. What is it? Permissivity. Okay. Moving on, obtain the expression for equivalent capacitance of two capacitors connected in series. Now for this, you definitely need to derive this expression. So they are given that we need to find equivalent capacitance for two capacitors connected in series. So these are my two capacitors connected in series, correct? And let's say we have this. Understood? So the capacitance is C1, let's say the capacitance is C1. Charge is Q among both of these. Now I know that whatever voltage is given in series, voltage divides, correct? So for capacitance, we have Q equals to CV, correct? So C1 is given by Q by V1, correct? And C2 is given by Q by V2. And if we find the value of V1 will be Q by C1 and V2 will be Q by C2, correct? For series, we can just add V1 plus V2. The total voltage will be given, that is the equivalent voltage will be given by the addition of these. That is the total voltage in series, correct? So that will be charge divided by C equivalent of series. This will be Q divided by C1 plus Q divided by C2. So this is basically the expression. This Q will cancel out. This will be C1, C2, C2 plus C1 equals to 1 by CS. So CS will be given by C1 plus C2, C1 into C2. Correct? This is the required expression. Correct? Moving on to the next question. It says, 31st question, explain the conversion of galvanometer into an ammeter using relevant circuit diagram and expression. So ma'am, we know that a galvanometer can be converted into an ammeter very easily by connecting a small resistance in parallel with the galvanometer. So something like this is my galvanometer, and if I connect a small resistance with it in parallel, so let's say this is I, this is IG, this will be let's say S or R, whatever you want to call it. So this will be IS and this will be again I, correct? So Galvanometer can be converted into an emitter by connecting a low resistance in parallel with it. If you want to convert galvanometer into a voltmeter, then what you have to do? Mention down in the comments, okay? 31st question, what do you have to do to convert a galvanometer into a voltmeter? Okay? Okay. And here I is the maximum current, Ig is the current through galvanometer for its full scale deflection. This is galvanometer, and R is a low, or S whatever is a low resistance, and G is the resistance of galvanometer. Okay, we are already done with 31 questions and it's just been 30 minutes. Okay, write any three differences between diamagnetic and paramagnetic materials. So it's very easy. Diamagnetic are weakly repelled by magnetic field when they are placed inside a magnetic field. Paramagnetic are weakly attracted by magnetic field. So based on that, they have magnetization and permeability. See, they are weakly repelled by magnetic field, weakly attracted by magnetic field. Because of that, their magnetization is low and negative. Their magnetization is also low but positive since they are attracted by magnetic field. Relative permeability is less than 1, and for paramagnetic it is more than 1. Correct? That is it. Moving on to the 33rd question, it says, derive the expression for the motional EMF induced in a conducting rod moving perpendicular to a uniform magnetic field. So what we are given? We are given with a conducting rod. Okay, this is my conducting rod, correct? And there, okay, let's not make the conducting rod first. They are given that the magnetic field is perpendicular. So let me just take the magnetic field into the plane of this board, okay, and then we'll take a rod which is moving perpendicular to the direction of this magnetic field. How? Let's say this is my rod, okay, this is my rod, let's say P and Q. So P or Q, okay, so this rod is moving perpendicular, so let's say it is moving in this direction. B is inwards, V is in this direction. So their angle is what? Their angle is 90 degrees. Now let's say what we do is we take this frame. So this is the frame on which this rod is moving. Correct? This rod is moving on this particular frame. So let me name this PQRS. Now ma'am, we know whenever due to this motion, whenever this rod will move, due to its motion, a flux will be generated, correct? A flux will be generated, and flux I know is B dot A, correct? So A is the area of this frame on which this rod is moving. That's why we took this frame, correct? So this is just BA cos theta. Now this theta is the angle between magnetic field obviously, but A is normal to the area, correct? This is my area, so normal to that will be inside, correct? It will be inside in the direction of magnetic field, and that will be the angle. Then theta will be what? Theta will be 0 degrees. So theta is 0 degrees. So overall this phi will come out to be B into A, correct? And this area, let's just say the length of this rod is L, and this frame, the length of this frame is X, correct? So this is just basically a rectangle, so area is L into X, correct? So phi will become what? Phi will become B into L into X. Up till here, is it clear? Okay, then we need to find the expression for motional EMF. So EMF is nothing but minus d phi divided by dt. We'll just put the values of phi, that was what? B L into X. Now B is a constant, the magnetic field is not changing, it is a uniform magnetic field. Length of the rod is definitely not changing, so they will come out of the derivation, this derivative, and d by dt of what is left? The X, the frame on which that rod is moving. It can move anywhere, we just took X for our reference. So this will be the derivative of X, or distance will be what? Simply velocity. So the motional EMF comes out to be minus BLV. That is it. That is the derivation. Correct? Okay. Moving on to the next question, it says, show that focal length of a spherical mirror is equal to half of its radius of curvature. Now we have studied this from our 10th class that focal length is half of the radius of curvature, but they are asking us to prove it. So we'll just take a spherical mirror and we'll draw the lines. So this is a parallel line coming and it will pass from focus something like this. Correct? Let's say this is my center of curvature and I'll pass a dotted line. What do you have to do? You pass a dotted line till that incident point. Now the main point. Let's just name this. This is M and we draw a very close straight line till near this pole already like almost negligible. So this NP is almost negligible distance, but because this is curved and we need a straight line, that is why we drew it. Now let's say it is incident on with of angle theta with the normal. Correct? So this is also theta. Now this whole is 2 theta, so alternating angle, this one will be 2 theta. Correct? And this one is just theta. So this angle, this and this angle will be same. So this will be just theta. So let's see in triangle what? In triangle CMN. 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 Correct? So my tan theta will be what? Tan theta will be perpendicular, that is MN divided by base, that is CN. Now MN, just write it MN for now, and CN. CN is what? Radius of curvature for us, because normal is passing through radius of curvature. Here let me write CN is minus R. Negative is just for the reference, because we know on the left hand side all the distances are taken as negative, and FN. FN is focal length. Correct? Now this is the thing I got. Since this theta is very small, so tan theta, we know for very small thetas will be equal to theta. So we can write theta equals to MN divided by R. Correct? Up till here. Okay. Similarly, we'll do for the triangle FMN. For triangle FMN. Now in this we have not theta but 2 theta. Correct? So this is 2 theta equals to, perpendicular is MN, base is FN. So that will be MN divided by FN. Correct? So since again 2 theta is again very small, so this we can easily write 2 theta equals to MN. Now FN was F, that is focal length. So 2 theta equals to MN divided by focal length. Now even if you take negative sign or not, it won't make any difference in our final calculation. So that doesn't matter. Okay. So we have the value of theta, that is MN by R. Can I put that in here? So that will be 2 into MN divided by R equals to, what is it that we found? MN by focal length on our right hand side. Correct? So MN will cancel out. 2 divided by R equals to 1 by focal length, and if you just invert it, focal length will be R by 2, which proves our point that focal length is half of the radius of curvature. Okay? We are again done with one more derivation. Let's move on to the next question, that is 35th question. Now, okay, let's see. The work function of cesium is given. This given as omega is given as 2.14 electron volt. Calculate the threshold frequency for cesium. Threshold frequency for cesium. Now this is very simple. We know omega is h nu naught, where nu naught is the threshold frequency. H is Planck's constant, which is 6.6, 10 raised to power minus 34. This nu naught we have to find, and this omega is given as 2.14, but it is in electrovolt and this is in joule per second. So to convert this in joule, we'll just multiply 2.14 with 1.6 10 raised to power minus 19, and this will be joule, divide by 6.6 10 raised to power minus 34 equals to our nu naught. So this will be the answer. You can just solve it. I think you will get something around 0.51 into 10 raised to power 14, or I guess minus 14, something like that. Let me just check. Okay, you will get 5.1. The answer will be 5.1 10 raised to power 14 hertz will be your threshold frequency. More than this frequency, you will need to eject electron out of cesium. Correct? Okay. 36th question then says, mention 3 features of nuclear force. Now we have studied nuclear force, very easy. We know that it is the strongest force in nature. Nuclear force is the strongest force in nature and holds protons and neutrons together inside the nucleus. It is charge independent. Charge independent nuclear force acts equally between proton-proton, neutron-neutron, proton-neutron pairs. Unlike electric charges, they only attract between unlike and repel the like pairs. This happens equally between like as well as unlike pairs. Then there are short range forces. They won't act like gravitational force act between planets. They won't act between planets or even two charges which are separated by a long distance. Long is thodo. This is 10 raised to power minus 15 meter. It acts only over very small distance, about 10 raised to power minus 15 meters. Okay. Okay, moving on. Okay, we are moving towards 5 marker questions. The first question is, derive an expression for the electric field at a point on the axis of a electric dipole. So we are asked for electric dipole. We'll make an electric dipole. This is, let's say, my charge minus q. This is plus q. And the distance between the centers of these dipole is 2a. Basically, this is 2a, and from the center this is also a, this is also a. Now they have asked at a point on the axis. So let me take a point on the axis of this dipole. This is the axis of the dipole. So if I extend it, this is on the axis. Correct? So on the axis, the distance from center till this point is, let's say, this is r. Understood this whole diagram? So from plus q, the distance till that point will be r minus a, and from minus q, the distance will be r plus a. Very simple, nothing much, just a lot of lines, but nothing much. Okay, so we need to find electric field at that point due to this dipole. So what we'll do, we'll find electric field due to plus q, electric field due to minus q, and we will find the equivalent electric field at that point. So electric field due to minus q will be what? K, that is our constant. Q divided by what? The distance, square of the distance. So from minus q, the distance is r plus a, that is r plus a whole square. Due to plus q, okay, q divided by r. Now the distance from plus q is r minus a. So this is r minus a whole square. Now definitely this charge is closer to point P. So the electric field due to plus q will be definitely more than minus q, and electric field due to plus q will push it push away from it, but minus q will pull it towards it. So they will definitely be subtracted instead of addition. Correct? So let's see the equivalent, what equivalent electric field will be. That will be electric field due to plus q. So definitely due to plus q, electric field will be more since it has lower distance, and due to minus q it will be less. So kq divided by, due to plus q we had electric field r minus a whole square, r minus a whole square, minus kq r plus a whole square. Correct? So we'll just take KQ common. This will be R minus A whole square into R plus A whole square if we take the LCM, and this will be R square plus A square plus 2R is just basic math, minus R square minus A square plus 2RA. Correct? So this will cancel out. We will get KQ. Now this will we get 4RA, but sorry, in here if you just apply basic math, this will be R square minus A square whole square. Correct? So we got what? We got K, that is our constant. If I write 2Q, correct, into A into 2R, okay, divide by R square minus A square whole square. So this 2A into R, this will be my dipole moment. We know dipole moment is the charges into distance between those two charges, that is 2A. So 2A into Q will be dipole moment, that is Kp into 2R divided by R square minus A square whole square. And this is, my friend, is the electric field due to the whole dipole. Correct? Understood? Okay. Next question says using Kirchhoff's laws, arrive at the balancing condition of Wheatstone network. Now let's see what Wheatstone network is first. So I have something like this. This is a Wheatstone network, or you call it Wheatstone bridge, something like this, and it is connected with a voltage source. So this is the voltage source. Now a current is moving, and since it's a parallel circuit, current will divide. This goes I1, and let's say this is I2. Let's name it P, Q, R and S, and this is the main point. This is the main thing. Okay, so a current is flowing through this part, and this is just our resistance. Now we need to see the balancing, arrive at the balancing condition of Wheatstone bridge. So what we do, we use Kirchhoff's law. So for Kirchhoff's law, we need to see in what direction we'll apply the Kirchhoff's law. We need to see the direction of the loop. So we'll use, you can use any loop there, it doesn't matter. Just do the calculations very carefully. Okay, so in the loop, okay, let's name it A, B, C, D. Okay, so in the loop A, B, D, A, loop A, B, D, A, that is A, B and this D and again A. So current is going in this direction, and we have taken the loop in the direction of current. So that will be I1P plus Ig into G, Ig into G. But this is opposite to the direction of current, so that will be minus I2 into R equals to 0. This is my first equation for the loop AB DA. Now for the loop, second loop, that is BCDA. BCDA. Loop BCDA, we will see the direction of current. It is taken something like this. That means now this is I1, Ig went here. So here I1 minus Ig left, and Ig joined I2 here. So this is I2 plus Ig. Correct? So with the Q, the current is I1 minus Ig. I1 minus Ig into Q. Then this is in the opposite direction. So that will be minus of I2 plus Ig into the resistance is S and then minus of Ig into G, and this will be equal to 0 with our second equation. Correct? Okay, now for balancing condition, we know that no current passes in this center wire, so Ig will be 0 for only balancing condition. So we'll put 0 everywhere, this becomes 0, okay, this becomes 0, then this whole term becomes 0, this becomes 0. What is left? Left is I1P minus I2R, I1P minus I2R equals to 0. This was my first condition. Second, I1 minus this also becomes 0. So I1Q, then minus I2S and equals to 0. Correct? This is my second equation. Okay, if I find I1 by I2 in first condition, I1 by I2 will be what? R divided by P, okay, and I1 and I2 from here, I1 divided by I2 from here will be S divided by Q. And if I equate these, because both are I1 by I2, so that will be R by P equals to S by Q. This is the balancing condition. Using Kirchhoff's law, I arrive at the balancing condition. For balancing condition, Ig equals to 0, and this is my required balancing condition, that is R by P, or you can write P by R equals to Q by S. Correct? Let's move on to the next question. That is 39th question. We are only 7 questions away. Okay. State and explain Ampere's circuital law. Then we'll move on to the second. Let's just see what is Ampere's circuital law, because it's a big one. So it states that the line integral of a magnetic field around any closed path. So let's say I have a closed path. So the line integral, simple integral over a closed path of magnetic field. So this is B dot dl, understood? The line integral over a closed path of a magnetic field is equal to mu naught times the total current enclosed by that whole path. Understood? And mathematically we also understood it the same. B dot dl, their line integral over closed path equals to mu naught into I enclosed by that path. Here B is magnetic field at that point, dl is some length element along that closed path, small length element, then mu naught is the permeability of free space, and I enclosed is the net current enclosed by that loop. Now the second, they say derive the expression for the magnetic field at a point due to an infinitely long straight current carrying wire using Ampere's circuital law. Okay, so I don't have an extra sheet. Let me just squeeze it here. Yeah. So they are asking derive the expression for the magnetic field. So we have infinitely long straight current carrying wire and the expression for magnetic field at a point. This is a point, let's say. So I is in upwards direction. Okay, so what we'll do, we'll make a closed path around this wire, and this is the exact path in which magnetic field will be there around this straight wire. We know it is in concentric circles. So at this particular point, magnetic field will be in the direction of tangent. Correct? So we take a small length element at the point, at that single point. So at that single point, what was the Ampere's circuital law? B dot dl equals to mu naught into I enclosed. Correct? And we need to find the expression for magnetic field. So this B dot dl can be written as this B is around this wire in this closed path. This B is not changing. Correct? So B we can take out from the integral. dl equals to mu naught into I enclosed. Now this is dl is, let's say, the radius of this closed path. So dl will be what? The circumference of this closed path. Correct? So this will be simply 2 pi d, and this is mu naught into I enclosed. So B will simply be mu naught I divided by 2 pi d. That is it. This is the expression of magnetic field at that point due to an infinitely long straight current carrying wire using Ampere's circuital law. Done? Okay. Moving on to question number 40th, it says derive the expression for refractive index of the material of a prism in terms of angle of prism and angle of minimum deviation. So we have to find just the expression of refractive index in terms of these two angles. So for that, let us just draw the prism and draw it neatly and use a lot of space of your paper, it's fine, but we have so many angles in this diagram, right? So make sure you are drawing this diagram very neatly and a decent size, okay? So this is my prism. Now, right, this is the incident ray, refracted ray and emergent ray. For incident angle, I will write I1. This refracted angle with the, this is normal. This is my normal. So, this is R1. Inside the prism, all the angles we are taking to be R. So, this incident angle will also be R2 and this emergent angle will be taken as I2. Correct? Now some of the more things we have to do here. We have to extend this incident line and we have to extend this emergent ray. The angle between the incident ray and the emergent ray will be what? It will be angle of deviation. Correct? And this is my angle of prism. Let's just name these A, B, C, K, let's say M, and you can name this O, and let's say we name this N. Correct? Now we'll go step by step. Correct? First, let's look at this particular diagram, that is NKM. NKM. What diagram? This one. This is N and this is K, this is M. We'll look into this diagram. Now, in this diagram, what is this angle? What is this angle? This whole angle is I1 because of opposite angles, and this whole angle from here till here, this whole is I2, reciprocal angles. But this one will be what? Now I1 minus R1, correct? And this only will be I2 minus R2. Understood? Now in this triangle NKM, we are using external angle property because that is how we can decide the expression for delta. So by using external angle property, delta will be equal to the sum of these two angles. Correct? So delta is equal to I1 minus R1 plus I2 minus R2. Understood? So delta will simply be I1 plus I2 minus R1 plus R2. This is my first expression. Okay? Understood? Now moving on to a second expression that we'll see in the quadrilateral AKOM. Correct? In the quadrilateral A, K, O and M. Now in quadrilateral, that is AKOM. What was it? See, simply we have this ray, this is the prism diagram. So in the quadrilateral A, K, O and M, this is the extended normal. Now since this is the normal, so the angle, this whole angle will be 90 degrees and this whole angles will similarly be 90 degrees. So in this whole quadrilateral, sum of all the angles, angle A plus angle K plus angle O plus angle M will be what? It will be 360 degrees. Correct? And since K and M are 90 degrees, so angle A plus angle O will be equal to 180 degrees. Correct? This is my second expression. Now we have to look into this third diagram, third triangle, that is K, that is M and O. K, M and O. This diagram, can you see? So the sum of all the angles will be what? 180 degrees. So R1 plus R2 plus angle O will be 180 degrees. So second is R1 plus R2 plus angle O is 180 degrees for the triangle KOM. Okay, understood? We are going step by step. So this will also be angle. Now okay, so this whole equation is equal to 180, this whole equation is equal to 180, so we can equate them. So that will give us angle A plus angle O equals to R1 plus R2 plus angle O, correct? So angle O cancels out. Angle A, that is angle of prism, comes out to be R1 plus R2. This is my third equation. Understood? So we have three equations. Angle A equals to R1 plus R2. This is angle A plus angle O 180 degree. And very important equation delta, that is angle of deviation, equals to I1 plus I2 minus R1 plus R2. Now they are asking, this is angle of deviation. They are asking for angle of minimum deviation. In case of minimum, for minimum deviation, for minimum deviation, there is a condition, that is I1 equals to I2, that is angle of incidence is equal to angle of emergence, and we'll take it as simply I, and both the refracting angle R1 equals to R2 equals to R, that is the first angle of refraction and then the incident angle of this refracted ray inside the prism will be equal, and this incident angle and this emergent angle, that is I1 and I2, will be equal, correct? So we have this condition. Let's put this condition in equation third and equation 1. Okay, so equation 1 was I1 plus I2 minus, now this was R1 plus R2, but we saw that A equals to R1 plus R2, correct? So can I put that in this here, in this equation, that is I1 plus I2 minus A. This is another equation that I got. And since for minimum deviation, I1 equals to I2 equals to I, so this will become 2I. So delta is simply 2I minus A. From here, okay, let's just keep it till here. This is one of the main equations that will need after. Okay, let's name this as A equation. Okay, then the another equation we had, I told you, very important, this one, that is angle A equals to R1 plus R2. Now for minimum deviation, R1 equals to R2 equals to R, correct? This is the condition. So angle A will become 2R, and from here, okay, again this is the main equation. Let's just keep it here for now. Now they are asking us to find, what? They have asked us to find the expression for refractive index. Now refractive index at this point will be what? I1 into, not I1, let's say the refractive index of the outer medium is mu1 and inside it is mu2, correct? So this refractive, the Snell's law at the point K, at K, Snell's law, we are applying Snell's law. So Snell's law will be what? Mu1 into sine I1 will be equal to mu2 into this refractive index angle, that is sine R1. Is this understandable? Okay, till here everything is true. So they have asked us to find the refractive index, that's why we have used this formula. Now let's just write this formula again. So we have a formula that says mu1 into sine I1 equals to mu2 sine R1. For minimum deviation, we have taken I1 as I. So this is mu I equals to mu 2 sine R. Correct? Understood? Now we just have to put these values. Now from here, can we find the value of I? That is, from here I will be what? I will be delta angle of minimum deviation plus A, that is angle of prism, divided by 2. Correct? Understood? Then from this equation, from this particular thing, we have R equals to angle A divided by 2. Correct? So we have I and R here. Just put these values in this particular equation. We can write mu 2 divided by mu 1 equals to sin I divided by sin R. Sin I is this, sin I is delta minimum plus A divided by 2 divided by sine of R, and R is A by 2. R is A by 2, and hence this is the formula for, this is the expression for refractive index of prism. Correct? Understood everything we did step by step. First, we looked into this triangle with external angle property, then we went to this whole quadrilateral, then this the below triangle. Okay, so from all these two, just using simple geometry, nothing much physics in here, just need to remember this particular condition, that for minimum deviation I1 equals to I2 equals to I and R1 equals to R2 equals to R. Put these values in the equations given, and then this is Snell's law. Using Snell's law we can find refractive index. Done? Okay, moving on to 41st question. Oh, we have a solution here. Explain the formation of energy bands in solid. So what is happening in mainly for isolated atoms, electrons are chilling in their orbitals, but for solids we know atoms come very close. When these atoms come very close, their valence band overlaps, and the electrons in those valence bands again overlaps. Now since they were having discrete energy levels before overlapping when they were isolated, but now lots of valence bands are overlapping. Because of them, due to the discrete energy levels, all of the energy levels gets combined and we get an energy band. Let's just read it. In an isolated atom, electrons have discrete energy levels. Correct? When a large number of atoms come together to form a solid, the outermost atomic orbitals, that is our valence orbitals of neighboring atoms, they overlap. Correct? This is the atom and this is the atom, and these are their valence bands. So what they are doing, they are overlapping. Correct? Due to this interaction, each discrete energy level splits into a very large number of closely spaced energy levels. Since a lots of energy levels overlapped each other, so they split into very large number of energy levels and which are closely spaced. Okay, till here it's fine. Now these closely spaced levels, they merge to form a continuous range. Now they are very closely packed, so instead of having discrete energy levels, they form a continuous band. Okay, they form a continuous ranges of energy called energy bands. Correct? There are two most important bands we know. One is valence band, one is conduction band. For valence band, they are highest occupied. So this is the diagram. This is my valence band, and below it is conduction band. This is the highest occupied energy band, and conduction band is the energy band above the below the valence. Okay. Sorry, this was the conduction band. Above we have conduction band, below we have valence band. My bad. So energy band above the valence band, where electrons can move freely and conduct electricity. So all the electrons that are there in this conduction band, they can move freely, and due to the electrons in the conduction band, we say that they can conduct electricity because they are moving freely. Correct? The energy gap, this is the energy gap between valence band and conduction band. It is depicted as Eg, and it is forbidden. No electron can exist between this space. They can either be in valence band or they can either be in conduction band. Now this energy gap we know is different for conductor, semiconductor, insulator, right? And that is what they have asked in second part. On the basis of energy bands, distinguish between a conductor, a semiconductor and an insulator. So let's just see. So on the basis of energy band, their band gap for conductor is 0 because the conduction band, and this is somewhat the diagram of conductor. So this is my valence band, this is conduction band, this is the conduction band, and this is the valence band, and we can clearly see they are overlapping. So their band difference is, energy gap is 0. For semiconductor it is very small, but for insulator it is very, very large. That is why it is hard for electrons to jump from valence band to conduction band in case of insulators. Okay, valence band and conduction band, again they overlap, they are separated by small gap, they are separated by large gap. Electrical conductivity, since electrons can easily travel to conduction band in case of conductors, so conductivity is very high. That is moderate because the difference is not much. See, this is, let's say, the difference of semiconductors, and this is then the difference of insulator. Insulator, semiconductor, valence band, conduction band, valence band, conduction band. So since the energy gap is not much, by giving small temperature, in case of semiconductors, electrons can easily jump from valence band to conduction band. But in case of insulators, even after giving temperature, the gap is still very high. Electrons don't have this much energy to jump from valence to conduction band, and that is why their conductivity is very low. Some of the examples for conductor, they are copper, aluminium. Of the wires we used silicon, germanium. With semiconductors chapter we have read about these, and then glass and rubber, we know they don't conduct electricity at all. Okay, one more way you can write this difference for conductor, again the same, valence band, conduction band overlap, no energy gap, large number of free electrons are available in the conduction band to conduct electricity. Electrical conductivity is very high. Valence band and conduction band are separated by a small energy gap. At room temperature, some electrons can jump to the conduction band. Conductivity is moderate and increases with temperature. Examples are silicon, germanium. For insulator, valence band and conduction band are separated by large energy gap. Electrons cannot easily move to the conduction band. Electrical conductivity is hence very low, and the examples are glass and rubber. Okay, now you have two kind of ways you can write your answer. Moving on to 42nd question. Now these questions are 5 marker questions. You have to attempt any two. They will be given 3 questions, I guess. Okay, 3 or 4 questions. Okay, 3-point charges 3 nanocoulomb, -2 nanocoulomb and 4 nanocoulomb are placed at the vertices A, B, C of an equilateral triangle of side 0.2 meter. Calculate the potential energy of the system. And then we have to calculate the amount of work required to place the same charges at the vertices of an equilateral triangle of side 0.1 meter. So now they have changed the side. So let's just draw the diagram first. This is somewhat my diagram, correct? This is an equilateral triangle. A, B, C are the vertices. This has 3 nanocoulomb. This has -2 nanocoulomb charge, and then this vertex has 4 nanocoulomb charge. Correct? Now we have to calculate the potential energy of this whole system. Now this is very simple. At A, B and C, the charges B and C will produce some potential energy, will produce some force due to which will have energy, and same for point B, A and C will have an effect on this charge, and for C point, A and B will have their effect on that point. Okay, so simply for potential energy we'll just add the potential energies due to another charges at this point. So that is UA plus UB plus UC. Correct? So what is potential energy? Let's just take the constant as K for now. For this, the charges will be QB into QC divided by R square. Correct? At A due to due to C, plus then this will be K QB QC divided by R square plus K QC QA divided by R, okay, not square. Correct? So we have, okay, let me write this again, K QA QB divided by R plus K QB QC divided by R plus K QC QA divided by R. This is the formula for potential energy of this whole system. Correct? Now we can just take the K and R common, since R is same as this is an equilateral triangle. So the charges were what? -3 into 2 plus this will be -2 into 4, 3 into -2, yeah, plus -2 into 4 plus 4 into 3. Correct? And these are nanocoulomb. So we'll have to multiply 10 raised to the power minus 9 into 10 raised to the power minus 9, that is 10 raised to the power minus 18. Correct? So this will simply be K by R. If you calculate this, this will be -6, and this will be -8 plus 12 into 10 raised to the power minus 18. Now K is 9 into 10 raised to the power 9 and R is given was 0.2. So that is 9 into 10 raised to the power 9 divided by 0.2. This whole system, their charge will, their calculation will come out to be -2 and into 10 raised to the power minus 18. So if you just solve this, you will be getting, so you will be getting 9 into 10 raised to the power minus 9. Yeah, so you'll be getting -9 into 10 raised to the power minus 9 into this 10. So this whole calculation will come out to be -90 into 10 raised to the power minus 9 joules. Yes, correct? Till here everything is clear. Yes, now they have asked us, so we have calculated the potential energy of the system. Now we have to calculate the amount of work required to place the same charge at the vertices of an equilateral triangle of side 0.1 meter. So this all will be same, just the value of R is changing. For potential energy of the triangle having, this triangle is having 0.2 meter. The other triangle which is having 0.1 meter, for that everything will remain same, just the value of this R will change, right? So can we write 9 into 10 raised to the power 9 into -2 into 10 raised to the power minus 18 divided by, instead of 0.2 we will writing 0.1. That is it. So this will give 110 here, and this will be -180 into 10 raised to the power minus 9 joule. Correct? This is potential energy at 0.1 meter. This is the potential energy at 0.2 meter. So the work done to move the charge from 0.2 to 0.1 will be what? Simply work done will be energy at 0.1 minus energy at 0.2, final energy minus initial energy, right? So this is -180 into 10 raised to the power minus 9 minus of -90 into 10 raised to the power minus 9. This whole is joule. So this will be -90 into 10 raised to the power minus 9 joule. This is the work done that we'll have to do to move all the charges at a distance of 0.1 meter from each other from this arrangement, from 0.2 to 0.1. That is it. That is what they have asked. We have solved the question. Okay, let's move on to the next question. Any doubt if you have, you can write down in the comment section. Okay, 43rd question they have asked, calculate the power dissipated. We have to calculate the power dissipated in the 10 ohm resistor. This is the 10 ohm resistance that is given in the circuit. So for power dissipated, we need to first see the current, right? and we have two batteries that are parallel to each other, that are connected in parallel to each other. So we have to find the equivalence EMF, their equivalent voltage, and then their equivalent internal resistance and all. So let's start. What is the first thing? Okay, we are given, let's say, E1 as 2 volt, correct? R1 as 1 ohm. Understood? Then E2 as 4 volt and R2 as 2 ohm. Till here we are given, and we are given this resistance, this load, that is 10 ohm. Now what we need to find first, we need to find the equivalence voltage, correct? So we know just the formula for this is E1 plus E2 divided by okay, no. For this the formula is different, that is E1 R2 plus E2 R1 divided by R1 plus R2. This is the formula to find equivalent voltage when two voltage sources are connected in parallel to each other. Okay. So E1 is what? That is 2, R2 is also 2, plus E2 is 4 and R1 is 1, divided by R1 is 1 and 2, and this will come out to be 8 by 3. Correct? Now to find the equivalent resistance. Now these two resistances are connected in parallel, so we can simply write Rp equals to 1 by R1 plus 1 by R2, that is 1 by 2 plus 1, and this will come out to be 3 by 2, so Rp will come out to be 2 by 3. Correct? So we have EP as 8 by 3 and Rp as 2 by 3. Now to find the current between this wire, between around this load, what do we need? The total resistance. The total resistance in this wire is due to this load resistance, yes, but due to these two wires as well. So the formula for current will be what? It will be EP divided by resistance due to those two batteries, so two voltage sources, plus its own resistance. Correct? So EP was 8 by 3, Rp was 2 by 3 plus load resistance is 10. So 8 by 3 divided by 2 plus 30 by 3. So this will come out to be 1 by 4, which will be 0.25 ampere. So current in this wire is 0.25 ampere. Correct? Now they have actually asked us to find the power. So power will simply be I square R. Correct? 0.25 whole square into R is 10 ohm, and this will be 0.0625 into 10, and that will be 6.25 watts. That is the power dissipated across the resistor 10 ohm. That is clear? Is this all clear, my friend? This is the power that is being dissipated against the resistor, across the resistor 10 ohm. Correct? Okay. Moving on to the next question, that is 44th, an indicator and a resistor are connected in series. So an indicator we have, and we have a resistor, they are connected in series with a AC source. So this is my AC source, its voltage is 200 volt given, 50 hertz given, and the current in this circuit is given to be 2 ampere, and voltage leads the current by an angle. We are given the phase difference by which voltage is leading the current, that is pi by 3. Okay, we need to calculate the inductance of this inductor, that is L. Correct? We need to find L. Now let's think this in a reverse manner. We need to find L, that comes in the formula of XL, 2 pi f into L. Correct? XL, now we just need to find XL of this whole circuit, of this inductor. Correct? Now, do you know that tan phi equals to XL divided by R? Correct? We know that much. Phi is given. Tan pi by 3 is tan 60 equals to XL divided by R. So this is root 3. So we get XL equals to root 3 into R from this equation. Correct? From this formula we get XL equals to root 3. Now the total impedance of this whole circuit, that is Z, can be given by XL square plus R square. Correct? But we are given voltage and the current. So total impedance will be V by I simply. That is 200 divided by 2. So this is 100. So impedance of this whole circuit is 100 because we are given the current as well as the voltage of this circuit. Correct? Can I put that here? 100 equal to, now we have to find XL. So R was what? XL was root 3R, so R will be XL by root 3. So this is XL by root 3 whole square. This will simply be XL 4XL divided by 3 in the root. This is 100. So 100 will be 2XL divided by root 3 and XL comes out to be 50 root 3 from here. Okay, now we knew we have to find L from this formula. XL we have. Frequency is also given, that is 50 Hertz. So we'll just put the value of XL in that formula. XL equals to 2 pi F into L. L will be XL divided by 2 pi F. XL is what? 50 into root 3 divided by 2 into 3.14 into 50 Hertz. So this will all be cancelled out and you can do the calculation with the help of calculator. I think it will come out to be, yes, 0.276. L will come out to be 0.276. Don't forget the unit, that is Henry. Okay? Understood? The whole step-by-step solution you have understood, right? Okay, let's move on to the last question of our third model paper. Again, I'm telling you, if you do these 3 model papers that are available on our channel, you will be all set for your PU2 boards. Trust me. Okay. Last question says, in Young's double slit experiment, the slits are separated by a distance of 0.5 mm. As you read the question, write down the important points. So they are separated by a distance of 0.5 mm. Now we have to convert it in meter, very simple. That is 5 into 10 to the power minus 3 meters. So D is given. Then and the screen is at a distance of 1.5 meter from the slits. So D is 1.5 meters from the slits. If the distance of 9th bright fringe, the distance of bright fringe is given. So the distance of 9th bright fringe is given as what? 1.3 centimeter, which will be 1.3 10 raised to power minus 2 meters. Correct? Then from the central maximum is 1.3 centimeters. Calculate the wavelength of light used. We have to calculate the wavelength of light used and also calculate the distance of 5th dark fringe. We have to find the distance of 5th dark fringe here from the central maximum. Correct? Very easy. We simply know that the distance of 9th bright fringe, the formula for this will be what? N lambda D by D. Correct? This will be the simple formula. N is what? N is 9. Lambda we have to find. D is given as 1.5 and small d, distance between these slits, is given as 5 into 10 raised to power minus 3. Yes. Correct? So we'll simply cancel these out and the distance is also given, that is 1.3, but it is in centimeter, so that is minus 2. Correct? So this will come out to be minus 2 divided by, this will be 2.7. Just that into 10 raised to power minus 3 equals to lambda. So this will give you the value of wavelength of the light used. Its value will come out to be 4.8. You can definitely use the calculator, right? 4.8 10 raised to power minus 7 meters. This is the wavelength of light that is being used. Very simple. Now they have just asked us to calculate the distance of dark fringe. Now my friend, they have said dark fringe. So the distance of fifth dark fringe will be 2n minus 1 lambda d by 2d. Correct? So if you just solve this, just put everything, 2 into fifth minus 1 lambda, we just found out that was 4.8 10 raised to power minus 7, 10 raised to power minus 7 into d was what? 1.5 divided by 2 into, this was 5 into 10 raised to power minus 3. Correct? Just solve the powers of 10 first. This will be 9 and this will be 4.8. This will be 1.5 divided by, this will again be 10, and this whole power will be 10 raised to power minus 4. Correct? And if you do the calculation, you will get the value as 6.48 into 10 raised to power what? Minus 3 meters. Correct? You can solve this with the help of calculator easily, and you will get the value of fifth dark fringe, distance of fifth dark fringe from central maxima, that is 6.48 10 raised to power minus 3 meters. Okay, that is it. We are done with model question paper number 3. I hope all your doubts are cleared. If you do these three model papers, again I'm telling you, you are all set for your PU2 boards. Also, we have question bank solutions, question bank lives on our YouTube channel. You can go watch them chapter wise if you want. And that is it for this video. We'll meet in the next one. Till then, prepare for your boards. It's a great time for you to focus on your studies now. So till then, bye bye.